We often think of nuclear explosions as entirely destructive. In our media, they are the sum of all fears. A scorching death from which there is no escape. The harbinger of a desolate, post-apocalyptic future. In the real world, we fear them as the ultimate cudgel a despot could wield. A desperate weapon of last resort that only a madman would countenance using. A technology with the capability to wipe out all of mankind. An existential level threat. Nowadays, there are motivated efforts to disarm nuclear powers, to monitor and constrain the proliferation of nuclear weapons, to put Oppenheimer's genie back in the bottle. But in the late 1940s and early 1950s, even as scientists sought to expand the US's stockpile of destructive nuclear ordnance, they also realised that the flash of a nuclear detonation could illuminate the dark corners of our understanding of nature, and finally reveal one of its elusive building blocks. Today we will discuss how some of the most iconic physicists of the 20th century planned to use the nuclear bomb not to intimidate and incinerate, but to solve a confounding riddle of radioactivity and to hunt down a particle physics poltergeist. During the early decades of the 20th century, when radioactivity was first being explored and the structure of the atomic nucleus unravelled by the experiments of Ernest Rutherford and others, nuclear beta decay was observed to cause the transmutation of an atomic nucleus of one element into the atomic nucleus of another with the emission of an energetic electron. Physicists knew that a definite amount of nuclear energy was released in each decay. According to Einstein, the difference in mass between the initial and final states multiplied by the speed of light squared. They also knew that according to the law of conservation of energy, that energy had to be shared between the recoiling nucleus and the emitted electron. If a nucleus at rest decays into two other bodies, these bodies have to fly out back to back with equal and opposite momenta, such that the momentum is conserved overall. Zero momentum before the decay equals zero momentum after the decay. Conservation of energy and momentum dictates the exact energy that the electron should have in every beta decay. The energy of the electrons is fixed once the masses of the three bodies involved in the decay are specified. However, when James Chadwick measured the energy spectrum of the electrons produced in beta decay in 1914, he found that the electrons didn't all have the same expected energy. Instead, they showed a broad-ranging spectrum of energy, with the expected energy marking the upper bound of the distribution. This was an incredibly disturbing result. It seemed that energy conservation only held in a small handful of beta decays. In the vast majority of cases, energy seemed to be disappearing into the proverbial ether. Physicists at the time began to wonder whether the law of energy conservation held when considering nuclear processes. After all, it was already clear that mass was not conserved in such processes. Niels Bohr, among others, not for the first time, was ready to abandon the law of conservation of energy. Fortunately, Wolfgang Pauli took a more sober approach. In late 1930, Pauli endeavoured to save the law of energy conservation. Pauli proposed that when a nucleus undergoes beta decay, it is not transformed into the two bodies that had been observed so far, but three bodies: the final nucleus, an electron, and a new ghostly particle that had not yet been observed. This particle had to be electrically neutral to conserve charge in beta decays. It had to be at least as light as the electron, so as to reproduce the spectrum of electron energies in such decays, and it had to be very difficult to detect. Pauli's hypothesis suggested that the constant beta decay energy expected for the electron alone was really being shared between two light particles, and the electron was being emitted with the observed spectrum of energies without violating the energy conservation law. Pauli called this particle the neutron, the neutral one. However, Chadwick later applied this name to the neutral nucleon inside the nucleus, and Enrico Fermi renamed Pauli's hypothetical particle the neutrino, the little neutral one. However, despite the simplicity of Pauli's suggestion, the idea was met with skepticism by the wider physics community, and Pauli himself accepted that his hypothesis was a desperate remedy. Pauli was concerned that if his hypothesized neutrino really did exist, it should have already been seen in experiments. The fact that it hadn't been detected meant either that it didn't exist, or that detecting it must be extremely difficult, or even impossible. In a 1930 letter, Pauli wrote the following: "Dear radioactive ladies and gentlemen, I have hit upon a desperate remedy to save the exchange theorem and the energy theorem. Namely, there is the possibility that there could exist in the nuclei electrically neutral particles that I wish to call neutrons. But I don't feel secure enough to publish anything about this idea. I admit that this remedy may appear to have a small a priori probability, because neutrons, if they exist, would probably long ago have been seen. However, only those that wager can win." In the following year, Pauli admitted, "I have done a terrible thing. I have postulated a particle that cannot be detected." For now, Pauli's neutrino was a placeholder, a theoretician's sleight of hand to save the law of conservation of energy by proposing an invisible, untestable, unverifiable escape hatch. The community looked upon this idea of the neutrino with great skepticism. Niels Bohr rubbished the idea, but things were about to change. In 1934, Enrico Fermi formulated a mathematical theory for beta decay that has endured with little modification into the present. This theory postulated a new force behind beta decay and incorporated several brand new concepts. Dirac's ideas about the creation of particles, Heisenberg's idea that the neutron and the proton were related to one another, and crucially, Pauli's neutrino hypothesis. In Fermi's theory of beta decays, the weak force, so called because it's manifestly much weaker than the electromagnetic force, turns a neutron into a proton, and simultaneously creates an electron and an anti-neutrino. Fermi's theory was truly remarkable, because it accounted from first principles for all the observed properties of beta decay. It correctly predicted the dependence of a radioactive nucleus's lifetime on the energy released in its beta decay. It also accurately predicted the exact shape of the energy spectrum of the electrons produced in beta decay. Fermi's theory of beta decay and neutrino processes made accurate, quantifiable, testable predictions that consistently agreed with experiment. This success was taken as convincing evidence that a neutrino is indeed created simultaneously with an electron every time a nucleus disintegrates through beta decay. By the 1950s, few doubted that the neutrino must surely exist. All of its properties had been deduced, but only theoretically. Someone had to prove its reality. So how could the neutrino, if it existed, be captured? Almost as soon as Fermi's theory was formulated, Hans Bethe and Rudolf Peierls understood that Fermi's theory of the weak force suggested a reaction by which a free neutrino could interact with matter and be stopped. In 1936, Bethe and Robert Bacher noted, "It seems practically impossible to detect neutrinos in the free state, i.e. after they have been emitted by a radioactive atom. There is only one process which neutrinos can certainly cause. That is the inverse beta process, consisting of the capture of a neutrino by a nucleus, together with the emission of an electron or positron." Physicists were suggesting that if a beam of neutrinos, or more accurately antineutrinos, could be focused onto a matter target, some could be stopped by protons in the atoms of that target, changing those protons from protons to neutrons and emitting a positron, an anti-electron. There seemed to be a clear theoretical pathway to intercepting and detecting this ghostly new class of particles. There was a signal that could provide a smoking gun for the existence of these poltergeists. Neutrinos could be hunted. Unfortunately, this initial furore that the neutrino discovery was at hand quickly turned to frustration. As the name suggests, the weak force is incredibly weak. So weak in fact that the probability of inverse beta decay was calculated to be close to zero. A matter target would have to be light years thick before it would have a significant chance of stopping a neutrino, So despite having a theoretical mechanism for detecting the neutrino, making a positive detection seemed logistically and practically impossible. However, technology was soon to tip the balance with the advent of extremely intense sources of neutrinos. Physicists realised that if you could stream enough neutrinos through a matter target, even though the probability of an individual neutrino interacting is minuscule, the probability of any neutrino in a beam interacting would increase with the intensity of the neutrino beam. It turns out that two things changed the prospect of a neutrino detection in the 1940s and 50s. The creation of the most intense neutrino sources ever created in the form of fission reactors and fission bombs, and the intense drive of a young man from New Jersey to make his mark in the world of fundamental physics by harnessing the destructive power of the atom. That young man's name was Frederick Rains. Rains had become interested in mathematics and physics while studying at the Stevens Institute of Technology and during graduate studies at New York University, where he wrote a PhD thesis elaborating on Bohr's liquid drop model of nuclear fission. In 1944, during the height of the Second World War, Rains joined the Manhattan Project at Los Alamos and became a member of the theoretical division. Of course, the laboratory succeeded in producing, testing and delivering the first nuclear weapons in 1945, and during the late 40s and early 50s, Los Alamos' mission was intensely focused on building a reliable stockpile of fission weapons and developing the thermonuclear bomb. Rains himself was in charge of several projects, including Operation Greenhouse, related to testing nuclear weapons in the Pacific. However, later, the lab's focus started to shift. Rains recalls that Norris Bradbury, the director who took over from the infamous J. Robert Oppenheimer, lent enormous support to surrounding the nuclear weapons effort at Los Alamos, with a broad scientific and technological discovery program. Rains himself was part of the Bomb Test Steering and Liaison Group, a group interested in developing new experiments that could be mounted as part of nuclear weapons tests to study the intense flux of thermal radiation, neutrons and gamma rays produced by the bomb, and potentially harness them to address open questions in fundamental physics. Physicists realised that a nuclear detonation should produce a huge flux of antineutrinos for a very short time. Fissioning of atomic nuclei during the neutron chain reaction caused by a nuclear detonation gives rise to a host of unstable nuclei. Each fission event gives rise to an average of 6 beta decay processes, each producing a neutrino. Hence, a nuclear detonation produces an incredibly short but monumentally intense burst of neutrinos, a burst so intense that a few of those neutrinos could possibly interact within a detector located nearby. In 1951, Rains thought about using that intense burst in an experiment designed to detect the neutrino. After returning from the very successful greenhouse tests in Eniwetok Atoll in the Pacific, Rains became obsessed with the seemingly impossible challenge of capturing the elusive neutrino. In unpublished notes from a talk at Los Alamos in 1951, Rain recalls that the historic success of developing and testing the bomb at Los Alamos had been an exercise in thinking big, in the can-do spirit, and that can-do spirit permeated our thinking. Whenever we thought about new projects, the idea was to set the most interesting and fundamental goal without initial concern as to the feasibility or practical uses. We could count on the latest technology being available to us at Los Alamos as a result of the instrumentation needs of the weapons program, and that fact fed our confidence. After having been involved for 7 years in the weapons program, Rains asked Jordan Carson Mark, leader of the theoretical division, for some time to ponder such a neutrino capture experiment. In the summer of 1951, Rains mentioned his plan to capture the neutrino to Enrico Fermi and Hans Bethe. All agreed that the bomb was the best chance of finally pinning down the neutrino. A few months later, Rains was able to interest one of his Los Alamos colleagues in joining his quest, Clyde L. Cowan Jr. In late 1951, Rains and Cowan began Project Poltergeist, the first experiment in neutrino physics, an experiment to finally discover Pauli's infamous placeholder. So what did they plan to do? Well, Fermi's theory predicted that when an antineutrino interacts with the matter detector, it can transmute a proton into a neutron. So what Rains and Cowan needed was an intense flux of antineutrinos from the bomb and a huge tank of protons for them to interact with. Rains noted that our crude knowledge of the expected energy spectrum of antineutrinos from a fission bomb suggested that the inverse beta decay reaction would occur several times in a several-ton detector located about 50 meters from the tower-based explosion of a 20-kiloton bomb. Rains realized that scientists needed a massive, multi-ton tank of protons placed as close to a nuclear detonation as possible to have any possibility of detecting neutrinos. Rains and his collaborators therefore planned to build a gigantic liquid scintillation device, dubbed El Monstro. This device would be a daring extrapolation of experience with the newly born scintillation technique. In the 1950s, several groups discovered that transparent organic liquids rich in hydrogen emit flashes of visible light when a charged particle or gamma ray passes through them. Rains and his collaborators planned to use the newly discovered liquid organic scintillators as both the target for neutrinos, as these liquids had a high proportion of hydrogen, and the medium for detecting neutrinos. When a neutrino interacts with a proton in the scintillator via inverse beta decay, it would produce a positively charged positron, an anti-electron, and a neutron. The neutral neutron scatters about undetected. However, the positron quickly collides with an electron in the scintillator material and annihilates into two gamma rays that travel in opposite directions. These gamma rays Compton scatter off additional electrons, and the resulting energetic electrons crash into other electrons, creating an ionization cascade of charged electrons and scores of ultraviolet photons. The scintillator is a highly transparent liquid, toluene doped with terphenyl. When it becomes excited by absorbing the UV photons, it scintillates and emits visible photons as it returns to the ground state. The liquid scintillator is transparent to visible light, and these photons are collected by photon multiplier tubes lining the walls of the scintillation tank, where they release electrons from the cathode of a phototube and create an electronic pulse. So, if these light pulses can be detected, neutrino interactions in our detector can be detected. Neutrinos can be detected. The technology required to potentially detect neutrinos had recently become functional, and the first small liquid scintillation counters had already been developed. Indeed, one of those initial developers, F.B. Kiko Harrison, was even working at Los Alamos. However, the largest liquid scintillator detector created before 1951 had only had a volume of around 1 litre. To have any hope of capturing the neutrino, Rains and Cowan needed a massive tank of liquid scintillator, thousands of times that size. El Monstro, the monster, was an appropriate name for such a target and detector. However, simply building a massive, proton-rich target and detector wasn't the only problem that Rains and Cowan needed to overcome to have any hopes of capturing the neutrino. They also needed to ensure that the flux of neutrinos passing through their detector from a nuclear detonation was as high as possible. To ensure that was the case, they needed to get El Monstro as close to a nuclear detonation as possible. But how the hell can you place a particle detector 50 meters from a nuclear detonation? It'll be immediately vaporized. Of course, Rains and Cowan understood this problem, and Rains notes, anyone untutored in the effects of nuclear explosions would be deterred by the challenge of conducting an experiment so close to the bomb. But we knew otherwise from experience and pressed on. Rains and his collaborators proposed to dig a 150-foot deep, 10 feet in diameter shaft, 40 meters from ground zero. The bottom of the shaft was to be filled by a 75-meter long vacuum tank, and El Monstro would be suspended from the top of that tank. The top half of the shaft would then be backfilled to the surface. As detonation approached, the vacuum pumps would be powered up and would evacuate almost all the air from the vacuum tube. When the countdown reached 0, the connection suspending El Monstro was to be severed with a small explosion. For around 2 seconds, the detector would fall freely through the vacuum, seeing the bright pulse of neutrinos from the firestorm above and recording any electronic pulses, revealing their interactions with the falling detector. The earthen vacuum tube would shake violently around the detector as the blast wave passed, but El Monstro would fall serenely, undisturbed by the surrounding devastation. After the initial blast had passed, the detector would reach the bottom of the tank and land gently on a thick pile of foam rubber and feathers. Rains noted, "We would return to the site of the shaft in a few days when the surface radioactivity had died away sufficiently, and dig down to the tank, recover the detector, and learn the truth about neutrinos." This whole experimental scheme may sound insane, but it was not just the fever dream of over-exuberant scientists. El Monstro was granted approval by laboratory director Norris Bradbury in 1951. Bradbury didn't even expect the experiment to return a positive result. Theorists had calculated that El Monstro would only succeed in capturing neutrinos if neutrinos interacted with matter 10,000 times more strongly than anticipated by Fermi's calculations. However, the experiment could, at a minimum, determine that neutrinos interact with matter 1,000 times more weakly than limits set by previous experiments. So a null result would still catapult elementary physics forward and provide a stepping stone to larger, more sensitive experiments. Bradbury gave the green light. Rains noted that life was much simpler in those days. No lengthy proposals or complex review committees. It may have been that the success of Operation Greenhouse, coupled with the blessing given to our idea by Fermi and Bethe, eased the path somewhat. Rains's work on Pacific-based nuclear testing, twinned with the heavyweight support of titans in the field of elementary physics, seemed to have greased the wheels. In 1951 and 52, work started on building and testing El Monstro. The scintillation target consisted of a bipyramidal tank, about 1 cubic metre in volume, with 4 photomultiplier tubes mounted on each of the opposing apexes. The tank was to be filled with very pure toluene, activated with terphenyl so that it would scintillate. Tests with radioactive sources of electrons and gamma rays proved that it was possible to see charged particles traversing such a detector of almost any size, and Rains and Cowan began to consider logistical problems associated with scaling up the detector to a mass of many tons. At the same time, work was proceeding on drilling the hole that would house the experiment at the Nevada nuclear test site. El Monstro, the monster, was evolving and would soon be unleashed. So if all the technological roadblocks had been removed and El Monstro was in the process of being built, why have many of us never heard of it? Why is it not immediately recognisable in the annals of fundamental physics? Why is it not another landmark in the history of Los Alamos? Well, because the experiment never happened. On a fall evening in 1952, Rains and Cowan presented their El Monstro plans at a physics division seminar. After the meeting and late in the evening, a new, far more practical, far more sensitive method for hunting the neutrino was born. J.M.B. Kellogg, leader of the physics division, urged Rains and Cowan to review using neutrinos from a fission reactor rather than a nuclear explosion to capture the interactions of the neutrino with matter. The possibility of using fluxes of neutrinos from reactors had initially been dismissed. Scintillation detectors were subject to background noise. Gamma rays and neutrons produced in the environment and by radioactive decay in the components of a scintillator detector can produce signals that mimic the interaction of a neutrino with such a detector. The neutrino flux from an atomic explosion would be thousands of times larger than that from the most powerful fission reactor, so the flux of neutrinos from a bomb could swamp any troublesome background signals with a massive but short burst of neutrinos. This would not be the case for lower fluxes of neutrinos from reactors. Any neutrino interaction signal would barely peak above the pesky backgrounds. So clearly the nuclear explosion was the best available approach, unless neutrino interaction signals and background fakes could be separated far more efficiently. However, while following Kellogg's prompts, Rains and Cowan suddenly realised how to do just that. As we discussed, the original plan had been to detect the positron emitted in inverse beta decay and the photons from the associated ionisation cascade, and use that as the smoking gun for neutrino interaction. However, the new idea was to detect not only the positron, but also the neutron produced during a neutrino interaction with the detector. After being produced in an inverse beta decay, the neutron bounces off surrounding protons and slows down. As it slows, it can be captured by a proton to produce deuterium, heavy hydrogen. However, Rains and Cowan realised that if cadmium atoms were added to the scintillator, the probability of a neutron being captured by an atomic nucleus was far greater, and planned to add cadmium salts to their scintillator detector designs. But why is capturing the neutron useful? Well, the capture of the neutron releases a characteristic 9 megaelectronvolt flash of gamma rays, and occurs a few microseconds after the flash of light from the positron-electron annihilation. Electronic circuits could be designed to detect this delayed coincidence signature. 2 flashes of light, each with a well-defined energy range, separated by microseconds. This dual signal was a far stronger smoking gun for the neutrino interaction, and also allowed neutrino interactions to be far more strongly discriminated from background noise. Interactions that could cause ionization cascades in the detector, but were not neutrino interactions. With this powerful technique in hand, Rains and Cowan realised that they didn't need the incredible neutrino flux of a bomb to swamp their detector and overcome backgrounds. Detecting the neutrino using the much smaller flux of reactor neutrinos became feasible. Cowan recalls that, instead of detecting a burst of neutrinos in a second or two, coming from the fury of a nuclear explosion, we would now be able to watch patiently near a reactor and catch one every few hours or so, and there would be many hours available for watching in a month or a year. Rather than being an exercise in grabbing all the neutrino interactions you could in 2 seconds, the hunt for the neutrino would become a comparatively tranquil and relaxed endeavour. The process would still require nuclear fission, but that fission would be steady, controlled, the result of a newly developed fission reactor. The future of energy was to be the future of the nascent field of neutrino physics. The bomb and its attendant destruction were no longer required. Rains and Cowan would use a scalpel rather than a hammer. The discovery of neutrinos using the flux from a nuclear reactor is what history remembers. After preliminary experiments in 1953 at the Hanford site in Washington state, Cowan and Rains moved their experiment to the Savannah River plant near Aiken, South Carolina. After months of data collection, the accumulated data showed about 3 neutrino interactions per hour in their detector. To be absolutely sure that they were seeing neutrino events, Cowan and Rains shut down the reactor to show that there was a difference in the rate of detected events when the nuclear reactor was operational and powered down. Their results agreed perfectly with the interaction rates predicted by theorists wielding Fermi's new theory of the weak interaction, and were published in the July 20th, 1956 issue of Science. Clyde Cowan died in 1974 at the age of 54. And in 1995, Frederick Rains was honoured with the Nobel Prize for his work in neutrino physics. The intense drive of that young man from New Jersey had left an indelible mark on the world and history of fundamental physics. This is the folk history of the detection of the neutrino that is recorded by science textbooks. But we now realise that that folk history was the culmination of many twists, turns, frustrations, rehashes, and revisions. In that folk history, El Monstro has largely been forgotten, a footnote in the history of Los Alamos, a fascinating but ultimately dead end in the annals of fundamental physics. The tale of El Monstro demonstrates just how far scientists are willing to go to unravel the mysteries of the natural world. Even in the expanding envelope of a fiery nuclear detonation, scientists can push the very envelope of our understanding of the universe. The hunt for the neutrino, just like the creation of the atomic bomb, engaged many of the finest minds of the 20th century. An enterprise and a laboratory that initially focused on conflict, destruction, and devastation also inevitably built up connections, collaborations, and programs of research that drove fundamental physics forward. They say that necessity is the mother of invention, and that in war, desperate times call for desperate measures, the development of radical new methodologies and technologies. Sometimes that same logic holds when unravelling the mysteries of particle physics. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.